Coffee milk, huh? And let's come right here. Okay. So you guys have a copy of this, so you don't have to. Thanks God. Otherwise, we'll take you for half an hour to sketch that. Can I guys walk you through what we have right now? If you remember, Matt, when we went to Boston Scientific, did you guys remember that big transformer? There was a big transformer sitting right next to, in between two panels. And in every building that we deal, every commercial, for the most part, commercial industrial building, good sized building, you're going to have, guys, two voltages in the US. You're going to have 480, 277, and 288, 120. Cool. The 480, 277, Karen, will be burning all your mechanical equipment, the air handling unit, the chillers, the cooling towers, the pumps, and what's not. And your lights through a lighting panel, all your lights, we burn them at 277. And then we need a special panel that's called receptacle panel so we can burn our receptacles, the 120 receptacles. We have to. Now, how are you going to get 120, 208 from 480 to 277? You need a transformer. What you're looking at is very typical in the electrical industry. Very typical. In the electrical room, Karen, we have something called HP, the high voltage panel, that feeds, this is the panel, that feeds a transformer. Do you guys remember that when we went to the electrical room in Boston? A high voltage panel that feed a transformer that transform the voltage from high voltage, which is 480 volt, 277, down to 288, 120, so we can feed our receptacles. Almost, Derek, every electrical room that you're going to walk in, you're going to have something similar to this. These combo. Panel, transformer, panel. Panel, transformer, panel. Panel, transformer, panel. Did you guys hear me? And why do we do this? Why do we do it? Because you have to get the 288, 120 in a three-phase system, right? How are you going to get 288, 120? You need a transformer. Okay, so can I get you guys, this is your electrical room. You have what we call a high voltage panel, which is 480. Feeding, and that panel, by the way, this is your main panel. This will be your main panel, like the switchgear in our case, the main panel, feeding other things, plus a feeder that goes to a transformer. From the transformer, we go into a lighting panel, a low voltage panel, which is feeding receptacles. Everybody understand what the combo that we have here? And then, what's your job, Karen? Your job number one is to size the transformer for this receptacle panel. We need a transformer. And after we come up with the size of a transformer, we need to size the overcome protection device for the transformer on the primary side. Then we need to size the feeder on the primary side of this transformer. Then we're going to go to the secondary side, guys, and we need to size the panel itself. Number 4 is the actual panel, the cover or the aluminum inside the panel. Number 4. Number 5 is the overcurrent protection device inside the panel. Most of the time they're the same, but they don't have to. So the panel itself, the overcurrent protection device. And number 6, guys, is the secondary feeder of the transformer or the main feeder of the receptacle panel. Can I get you guys to understand this one before you leave? Because every project that you walk in is going to have a combo of this. Every project. You know? Cool? Everybody understand what we have? We have a main panel that we typically call a high voltage panel because it's 480, feeding a transformer that feed a low voltage panel, which is 288, 120. In the project that we have, Karen, we have 2 of this type. If you guys remember, we have one for the receptacle panels that you guys are going to be circuiting soon, next week for it. Same combo. And we also, Derek, do you remember the 288, 120 bus duct for that industrial building that we have? How are you going to feed 288, 120 bus duct? Well, guess what? You have to do the same thing. So we're going to have a feeder from the main panel, feed a transformer that take the voltage from 480 into 288, 120. Instead of dumping the voltage into a panel, we will be dumping it into a bus duct, 288, 120. Cool? So that's how physically it looks like. Now, as a one-line diagram, guys, that's how it looks like in one diagram. High voltage, typically delta. We have delta Y transformer, 480 on the primary, on the secondary 288, 120. It's always three-phase, always three-phase. And then it bring a feeder into a panel. Here's my panel. The panel has a main, and you have a multiple branch circuit. And from the branch circuit, you feed that baby receptacle circuits. We feed our receptacle circuits. And you guys remember we put 6 receptacles in a commercial building in 120 amp circuits, right? 6 to 8. So that this will be 6 receptacles to 8 receptacles fed from that receptacle from that 20 amp branch circuit. Can you see that? That 20 amp branch circuit? And that, let's just say 6 receptacles. Okay, does everybody understand what we have here? We have a main panel, we call it high voltage panel, feeding a transformer that transforms the voltage to a lower voltage and bringing it down into another panel that's called receptacle panel or low voltage panel. So we can feed our receptacles. Adam, you will be a fool if you feed your lights, if you burn your lights at 120 when you have a 277 voltage. Why? Some of you will say, Chad, how about my my lights? Well, why am I going to feed my lights? Your light typically will be fed from where? The main panel, 277. Why is it important, guys, to if you have a higher voltage in your building, why is it important to burn your equipment at higher voltage? Efficient. Your equipment is more efficient if you have higher voltage across them. Cool? All right, before I leave this scenario, everybody understand, here's your one-line diagram. Here's how they're physically located, right? The riser. This is a physical location of them. That's how the riser is. And you guys, the numbers are the same. The numbers here, 1 through 6, are the same numbers 1 through 6 here. Everybody understand? The difference is riser, one-line diagram. So it tells you why we bother. Okay, so any comments, any question about what we have before we go ahead and do it? Everybody knows why we care, because every building that you walk in, you're going to size these. Derek, remember when we start dropping the receptacle, building our riser, and you asked me what size transformer do I need, Chad, right, for the receptacle balance? You had pick this. Well, based on what? Based on this calculation. Unfortunately, we haven't done the calculation. Now we're going to go back, guys, and review. Actually, we're going to size that transformer for our project as one of our examples. You'll see. So if your size is different, all what you have to do is just go put the right size. Okay. Any comments, gentlemen? Any questions? Everybody's cool with that? Okay, now, here's how you start with your sizing. Number one, I'm giving you the following. When we size things, Karen, we always start sizing everything based on the load, right? What type of electrical load do you need in this building? In this case, because we're sizing a receptacle, everything is based on receptacles. I'm telling you that we hired Adam for this commercial building or industrial building, and Adam went and installed 200 receptacle, duplex receptacle, like the one in front of you right here. And then he put a multi-outlet assemblies, a multi-outlet assembly. He put 60 feet of multi-outlet assembly. You get the wall, that right in front of you. Multi-outlet assembly. And this is continuous, where they're continuously will be used. Multi-outlet assembly, continuously used. And multi-outlet assembly, 70 feet of multi-outlet assembly that's non-continuously used. You guys have done 2 load calculation with your friend Chad. Remember when we did that calculation for the receptacle, we based them on the number of receptacles first, we do a calculation, then in multi-outlet assembly, right? So this is the electrical load that you have. That's my load. This is the most important thing. Based on the load, I need to size all these. Any comments, guys? Any questions about what we have? Does it make sense, Derek? What we have 200 receptacles, 60 feet of multi-outlet assembly, like the one in front of you, continuously used, which is important because if they're continuously used, we allocate for them different value than if they were not. Or simultaneously used. And multi-outlet assembly, 70 feet, non-simultaneously used. Okay, so, and what's my job is to take this load, that electrical load right in here, based on the load sizing, take this load and size the whole system. Cool? Am I the only one who's excited here or what? Okay, so let's go ahead. The first calculation that you need to do, guys, if you guys remember 220.14H and 220.14I from the NEC code book, these will tell you what we're going to be writing right now to size to do the calculation. So I'm going to go directly into the receptacles. The first section is for the receptacle. The second section is for the demand. The width, and Adam, you did this one in Excel sheet twice, 3 times, as a matter of fact. You did them for the residential, we did them for the commercial, you guys did them for me for the industrial. Nothing new here. So the receptacles, the code allocate, guys, 200 receptacles that Adam decided to put there. You allocate 180 volt for each volt amp for each receptacle. That's it, 180 volt based on NEC code book. I think 220.14H is the one that talks about this. Then multi-outlet assembly, simultaneously used. I have 60 of multi-outlet assembly, 60 feet. Multiply this one by code 180 volt amp. 180 volt amp, guys, they give every foot, they give it 180 volt amp if they're simultaneously used. The non-simultaneously multi-outlet assembly, non-continuously or non-simultaneously used, these are non-simultaneously used, not used at the same time. The allocated, here's what we do. We take the 70, we divide it by 5, and then we multiply it by 180 volt amp. What does that mean? For every 5 feet, do you guys remember that one from the code calculation that you did with Chad? If they're non-simultaneously used, for every 5 feet, you allocate 180. All this stuff is coming from 220.14H, I believe. Or I always get, can anybody verify it? I haven't been there for a while. So these are the calculations that you have to do, my friends. H is the fixed multi-outlet assembly, and I is a receptacle outlet. Thank you. That's what I want to know, which is which. I is the receptacle 180, and H is a multi-outlet assembly. Simultaneously used or non-simultaneously used. Everybody knows what simultaneously. You're using it at the same time. How do I know, Chad? I always wonder, guys, how do I know? You have mold and you have all this stuff, but you don't know. If you don't know, what do you do? What's the worst scenario? Assume they're simultaneously used. If you're in a project and you're sizing this project and you have multi-outlet assembly, and you ask them, are you guys going to use them at the same time? They say, we don't know, Chad. So what would you do? What's your assumption would be, Adam? Yeah, they're using them at the same time, right? You're engineers, guys. You're designers. People are looking for you for solutions, right? You have to make up a decision. And the customers don't have all the answers for you. So you assume the worst scenario and you run. So, but I'm telling you, here's 17 non-simultaneously used, 60 simultaneously. Any comments, any questions about the multiplication, guys, that we did? Does it make sense? Yes? No? Okay. Then, my friends, after you do all this, then you're going to add them up. Now, you're going to add all these up, and you're going to end up with 49.3 kVA. 49.3 kVA. I want to remind you, Adam, that I divided everything by 1,000, right? So because when we size things, a volt amp is meaningless, guys, when you size transformers, right? Power transformers, you need kVA. So that's what we're going to add them up, multiply and add them up. Then table 220.44, we have been there for the commercial project, guys. I want to remind you, this is not a new table for us, 220.44. Table 220.44, guys, it will tell you in a non-dwelling building, the receptacles in a non-dwelling building, the first thing K, leave them alone. So then you're going to take the 49.3 kVA and apply this demand on it, 220.44 demand. They call it a demand. The first 10 kVA, these are sacred, shall not be touched. The first 10 K, leave him alone. Anything after you take the 10 kVA, anything higher than 10 kVA, which is 0.3 minus 10 K, all these are Ks, guys, remember. You will multiply this one by 0.5. Why 0.5? Because the code says 0.5. And then, gentlemen, you're going to add them up. You're going to add them up, and you'll end up with a 29.6 kVA. And I'm not doing all the steps, guys. You're graduating now, right? So you multiply, you do this math, multiply by 0.5, add the 10 to it, you should come up with a 29.6 kVA. Any comments, Karen? Any questions? Comments, questions for that? So that's the demand load for the receptacles. You guys have done this in the load calculation. This is nothing new. When you did the Excel sheet, that's what we did for the Excel sheet for the commercial project as well as for the industrial project. Okay, so now this is the number that you're going to go to town with. This is the number that you're going to go to town with. Can you guys see that? Now this number, that's the number that you're going to go to town and find yourself a transformer. Based on this number, we're going to go find ourselves a transformer. Before I move in, any comments, any questions, guys? Comments, questions? Make sense? Yes, no? Okay. Now next, my friends, now next, we need to go size an actual transformer. Do me a favor, go to DeWalt 7-7. Make sure you know how to use that one. DeWalt 7-7. That will give you the sizes of all the transformers that we have. Okay. Here's that DeWalt. Can you guys see that page? 7-7. Everybody's good there? Adam, do you guys have them? So when you go to 7-7, you're going to find yourself, so we're going to, 29.6, my 29.6 kVA. This is my demand. Take him to DeWalt 7-7. And Derek, on the left side, when you look at 7-7, that says three-phase full load current amps. And it gives you the kVA. What's the next standard from 29.6 kVA? 30. Everybody got that? So the next standard is 30 kVA transformer. You go up, right? You're not going to go down. The next standard transformer that you need for this project is 30. How do you know it's 30? You go to the next standard. Transformer size. Okay? As long as we're here, guys, I would like you to look at the 30. For the 30 amp transformer, for the 30 guys, for the 30 kVA transformer, Derek, I would like you to look at the following. Under the 480 volt, the primary, and the 208 volt. Would you please give me the full load amp under each one of these? Go to the 30, go under the 480. What's the full load amp under the 480? Thank you. 36.1 amp. What's the full, the 480? Yeah, but I put it in the wrong location. What did they say? 36.1 amp. How about the 208? 83.3 amps. From this table, guys, from this sheet, it gives you the size of the transformer and the primary current and the secondary current immediately. And if you don't have if you don't have these two currents, how would you find these currents, guys? You take the 30 divided by 480 divided by 1.73, you should come up with this number, 36.1. Take the 30 divided by 2.8 times 1.73, you should come up with 83.3. But the table will give it to you right from the get-go to make it easier. Okay? All right, so that's basically the size of, so number one, the first thing that we did, Adam, the first thing is we need to find the size of a transformer. You guys remember in Revit, you drop the transformer and you have no idea why you drop it? Right? That's how you size it. Now the transformer is going to be 30. You go to Revit, grab a 30 transformer. If that was a Revit project, drop it into that location. Okay. I'm trying to tell you why am I harassing you with all this. Okay, now the second thing we need to do, number two, is the primary overcome protection device. So Adam, we size the transformer. We need to size the fuse or the circuit breaker head of the transformer. If you guys go to table 450.3b, which we were there many times, so we need to find, the first thing, since we're doing the primary, we need to find the full load current, 30 kVA. By the way, it's already here. Here's the number right here. 1.73 times 480, and that should come up with 36.1 amp. And it's already given there in the table. So, but that's how you do it if you do the calc. When you guys go to the table, this transformer has a primary only protection. On the secondary, there's nothing. There's one downstream. So we're going to multiply it by 2.5. So my multiplier would be 2.5 from table 450.3b. 450.3b, 2.5, multiply this by 36.1. If you do your math, you're going to end up with 90 amps. If it's what, then you take the 90 amps, take it to this table, to this section, I'll give you 90 amp circuit breaker. And if it's not, you're going to go down. The maximum circuit breaker that you can put is 90 amps. Any comments, guys? Any questions? Where did I get the 2.5 Karen from the table that you're looking at? So when you go to the table, guys, when you go to your table B, we're going to have primary and secondary protection. Primary and secondary protection 250. And we're going to have a current of 9 amps or more. So we're assuming the primary is going to be here and not on the secondary side, but way a little bit down, right? Down here. There will be one inside the panel. So I have primary and I have my secondary down. And we use the rule tab in between.
So you're just saying that this was supervised location and that's
No, this is non-supervised location. Are you on 450.3b or A?
oh, I was on A.
Yep, go to B. B. When you guys go to 450.3b, we were there, guys. I don't want to flash because we were there. 450.3b will tell you two locations: primary only protection, or primary and secondary. If you're primary and secondary, second line, that will get you a 2.5 multiplier. So here's the size of my fuse. Then, Adam, in your Revit schedules, when you guys build the Revit schedule, you're going to go there and put this 90 amp circuit breaker. So how is this related to the Revit, guys? We're going to size one for Revit right now. You're going to go to Revit and pick a 90 amp fuse and change the schedules into 90 on the primary side. Any comments, any questions? Karen, does it make sense? Yes, no? Okay, so we size the fuse or the circuit breaker on the primary. The second thing, Adam, to bring the power from the high voltage panel to the transformer, you need a feeder. We don't bring him in a water pipe, we bring him in a feeder, right? So you need a feeder. For the feeder, guys, to size that one for the feeder, we got the primary overconduction device. We use the same thing. The I primary is 36.1 amps. 36.1 amps. We already calculated that one. You go 1.25. We're assuming that's kind of over the life of that transformer, guys. We're assuming that there could be continuous load and what's not on this feeder. That's an assumption. And we multiply by 1.325. It's a good assumption. 36.1. If you guys do the math on that one, increase it, that'll get you 45.1 amps. From 45.1 amps, Adam, my friends, to 45.1 amps, you're going to take it, come over here, 45.1 amps. Take this one to 310.15 B16 and 75. You're going to end up with three conductors, number 8, AWG. This is the size the size and the number of my conductors. Now remember, you go to 75-degree column because it's three-phase. So I have three conductors. Why three? Why not four? On the primary side, guys, there is no neutral. It's a delta. So we need only three conductors. You know? You need three conductors. I don't need a neutral. I'm feeding a delta. Delta has only 3 wires. Cool? Any comments, guys? Any questions? Any comments? Any questions about that? Does it make sense? Yes? No? All right. Let's go to the receptacle panel sizing. Now, Adam, we sized the primary. We sized the transformer. We sized the primary overconduction device. And we sized the feeder. Now, next, we need to size the secondary conductor. The secondary conductors, or secondary, the panel. Number 4 is the panel. You're going to take the 30K VA, the same 30, divided by 1.73 times 4, times, what's the voltage on the secondary side? 208, 208. If you guys do your math on that one, you should come up with the same number, 83.3 amps. And Derek is saying, well, Chad, we already got this information from the schedule, right? Okay. We are sizing, remember, the receptacle panel size, LP, which is the low voltage panel, the 28120. Then we're going to multiply 1.25, assuming this will take care of the 1.25 guys of continuous load. I know receptacles are not continuous load and we derated them, but over the life of this panel, on the feeder, it's really nice to have 25% extra. It takes care of your voltage drop carrying, it takes care of your if you overload that panel a little bit, 1.25 times 83.3, and if you did this math, you're going to end up with 104.2 amps. And then you're going to take your 104.2 amps, take it to the wall 3-12. You guys have this copy of this. I made a copy for you. The actual panel size would be 125 amps. Everybody knows how to use 3.12, the wall 3.12 or 3-12? Yes, no? You guys have a copy. I made a copy, Matt, for 312 and 313. You have a copy of it. 125. Okay, cool. So this is Adam. This is the size of the copper inside this panel. Okay, so let's go to the next. Everybody's good? Yes? No? All right. Let's go to the receptacle panel overcome protection device. Now we need the overcome protection device, guys. We size the panel. We're going to size the overcome protection device from 450.3B. It will tell you the same thing, guys. We go 1.25, multiply that baby by that 83.3 because we're the secondary side. That will get you 104.2 amps. Take the 104.2 amps. Take this one to 240. This is 2, believe it or not. Take it to 240.6, and I hope you guys have been there. 240.6. When you go there, you're going to end up with 110 amps. You can go up. You don't have to, but you can go up. You go to the next standard, which is 110. Karen, typically it's a good idea to match the overcome protection device to the panel. But for the test and everything else, guys, you're going to go by this method. So you have your panel will be 125 amp panel, and the circuit breaker inside the main panel is going to be 110. Now, most of the time, you're going to find that since they're close, Derek, since the 110 and 125 are close in number, what the manufacturers will do is they make the overcome protection device 120. So basically, oversize it. They oversize it. Any comments, guys? Any questions about the overcome protection device? Okay, so now we need to go, so that's the overcome protection device. Now we need to go to number 6, which is the feeder between the transformer and the panel. The feeder between the transformer and the panel. Adam, I always say match overcome protection device. Match overcome protection device. That's the best way to do it. Match overcome protection device. So that's a piece of cake. When you match overcome protection device, my friends, you're going to have number 6, match overcome protection device. So I have 110, 110 amp. Go to 310 of 15 P16 under 75-degree column, and you're going to end up with number of conductor number 2, AWG, and insulation THHN. And how many conductors? Anybody can tell me how many? You need 3 at least for a 3-phase. Do you need a neutral? Yes. So you need 4 conductors, full neutral, 4 conductors, number 2. Up to 225 amp panel, Karen, it's a good idea to have full neutral. Did you guys hear me? Up to 225 amp panels, it's a good idea full neutral. Higher than 200 to 225 amp panel, you start cutting the 70%. Remember when we sized that 70%, you cut it by more than 200, you cut it by 70%. Okay, so did we I'm just trying to write the installation. If you guys will write the installation here, T, H, H, and I always like to write the installation for the conductors. There you go. So now we sized everything for this combo, gentlemen, ladies and gentlemen. Everything for this combo. All right, so Derek, good. Now let me take you back into where we started. So Kieran, now we size the transformer, we size the overconduction device on the primary side, we size the feeder, in the primary, we size the secondary feeder and the overconduction device of the panel, as well as the panel itself. So you're good to go. Now the next example that I have for you guys, we're going to size the receptacle panel for our project. The receptacle panel for our project. Now, Derek, I haven't done this example before, so sharpen your calculators because I need the number. I don't have the numbers, so I need you guys to do bunch the numbers for me. Cool? Everybody's good with that? All right. So, the next example is going to be where am I here? So we got that. Go all the way back, all the way. Okay, now I have example number 2, guys. I'm going to use the following, Karen. I'm going to use the calculation that we did for the industrial project, which is, if I find my Excel sheet here, so many calculation. Here you go, Excel sheet. All right, so I want to remind you, you guys are very familiar with that. Okay, here's my receptacle panel. Adam, you did this calculation for me. Do you guys remember the 7? Here's a calculation that we have just done. 180, all the calculation, derate by the first 10. Do you guys remember that? And you came up with this number. This is an already derated number. Did you guys hear me? Here's the 180 times the number of receptacles. If you're using quads, 80 times the number of quads. And then the sections, the 5 and the 1 section, these are multi-out assembly. We already did this math for our project. Can I guys can I have thumbs up? We understand, Chad. This math that we did at the beginning is already done. I know. I'm going to size it based on this. Yes. Yeah. It will change. Yes, absolutely. No, you're absolutely right, because we haven't cleared out the receptacle yet. But I'm going to size it based on 99, and the number 99, Adam, came from previous project. So I want to size it based on 99, which is close. And multi-out assembly, 80, coming also from the project. Okay. Now, here's the number that I'm going to use. My number, guys, right now is 71510. Everybody understand this number, where this number is coming to be? Now, are there any other things? Now, Adam, we have a dishwasher. They're picking a dishwasher at 240, right here, too. All the way. So the number that I'm going to be using, guys, is this number right here. The number I'm going to be using is 73910. 73910. Everybody understand why? I have 71510 for all the receptacles, and I dedicated a circuit for the dishwasher 2400. So I have to go size based on 73910. Can you guys remember this one? The number is 73910. Okay. So I'm going to go right here. So the load is 73190, right? Am I right? 73910. Cool. Is that everybody understand where this number came to be? This is volt amp. This is load. Load for industrial project. Here's my load. The first thing I'm going to do, Adam, is convert this one to a language that we all understand, which is 73.9 kVA. 73, let's put the 1, 2. This is the language that we understand. So this is 73.91 kVA. 73.91 kVA. Okay? Everybody understand what we're going to do now? Cool? All right, so now 7. Hi, Steve. Oh, yeah. Sure. So I have 73.991 kVA, right? So that's my kVA. Now I need to go, now I have not done this. We're going to go size and overcomputation device. Now, Adam, all this calculation and the demand, can you guys put something like this? All this done. And the size was 70, what was it again? Matt, remind me. 73.91 kVA. Can you guys just put right next to that one, all this calc, done. Just write, done by Excel. By Excel sheet. Okay? All this calculation done by Excel sheet. Garrick, am I making sense? This is already done, so we don't have to worry about it. So my demand is actually 73.91 kVA, already done. Everybody's good with that? All right, so now let's go size the 73 point. I have my 73.91 kVA. Derek, get me the size of that baby. What's your next standard? From page 7-7? Thank you, 75. So the next standard is 75 kVA transformer. So gentlemen, you grab a 75 kVA transformer, drop it for this project. I can't remember what we did in Revit. If we did, well, we still have to go revisit the calculation, remember. So I'm not worried tomorrow because you guys need to go plug in your actual receptacles after you design it. Okay, that's 75 kVA, guys, done. Okay, now after this, Adam, straightforward. So we're going to go find, now we found the size 75 kVA, drop it in Revit, and then you're going to start taking, I need somebody to help me with the calculation. kVA, divide this by 1.73 times 480. And oh, by the way, this is coming also from the sheet. Derek, why don't you give me this from the sheet right away? The full load amp for the two of them, because it's already there. 75, it's 208. This is 2.2 amps at 208 volt at 480 volt 90?
Yeah, 90.2.
amps. That's directly from the sheet, guys. You can get them. So when you do the math here, you should come up with 90.2 amps. Or you can get it directly from the sheet. You can see that the sheet will give you the same number. It's already done for you. Okay. Then, Adam, you're going to take the 2.5, multiply it by 90.2. Now I need somebody to help me. I need two people to do it, guys, because I don't have the math for that. So I need 2.5 times 90.2. 225.5 amp second. Yep. Okay. And then we're going to take the 225.5 amp to 240.6. And, yep, thank you. 225 amp and go down. Right? Here's the size of my transformer. Go down to 225. That's not bad over going down. It's not 0.5 amp. Cool. So the prime, now what's in it for you, Derek? You're going to go to Revit schedules when we do the schedules in a couple of weeks. Change the overcomputation device that feed that transformer to 225 if that's the size of your transformer, which is most likely is going to be around this size. Next, primary feeder. The primary feeder, I need the Matt, you need to give me a few things. What was the primary for this transformer again? Primary current. 90.2 amps. Then for feeder, we multiplied by 1.25, right? Parameter feeder. 1.25 multiply 90.2. Who's my calculator? Two people.
112.75.
112.75.8 amps. If they take 112.8 amps, take it to. I need two people, guys, here to help me with that. Take it to the wall. Take it to 310 or 15B16. And what is it?
Number 2.
I need. Do I have a second? Do I have a second?
Yeah, that's it.
Number 2. How many conductors? Thank you. Why 3? There you go. 3 conductors. Number 2. A W G T H H M. That's the size of my baby. Okay, so that's the size of my conductors. All right, let's go to the secondary size. I have my transformer was 75 kVA, 1.73 times 208. It was 28.1. The secondary, we looked at it here, 28.2, give or take, 28.2. So, Matt, if you end up with 28.5, you know what the difference is 1.732. They add the 2 at the end. So, don't sweat it too hard if you're slightly different. So, I need to size my panel. Cool. So, that you size it based on secondary. Then you're going to multiply it by 1.25 times 208.3. What was the size? I need 2 people to do the math here, please.
It's 260.25.
Yep. 60.25.3. Good enough? 260.3. Then you're going to take your 260.3 amp, take it to the wall 3-13. What's the standard? Any second?
Yep.
Okay, so 300 it is. 300. $300 amp panel. So your panel is going to be 300. If you guys look at what we did here, I thought that's what we got. We got it right here, and we came up with at 225. Here's my full load, and we came up with this number, 300. The only difference here is we should have first sized the transformer, because the transformer could be did. The reason why we exactly came with the same number here, guys, because the transformer size was very close to the actual size that we came up with, right? So 300. So we're good with that, 300. All right, so I have 300 amp. Everybody's good with that? 300 amp panel. Let's go down to receptacle panel. That was on overcap protection device. The secondary for overcap protection device. So we size the panel, receptacle panel. So we have this size of panel. Number 5 would be the receptacle panel overcap protection device. What did we do? We took 1.25 multiplied by 208.3. What did we come up with at second level?
260.25.
260.3, right? Is that what it did?
Yep.
The beginning? Have short memory. 260.3, okay? Then you're going to take the 260.3 amp to the walls. Do we have 275 or do we have to 300? 300. We don't have 275. 300. So my next standard, guys, from 240.6 is 300. My next standard is 300. Same match the overcap protection device. 300. We have 250. We don't have 275. So You go next to the next standard, which is 300. So up, 300 amps. Okay, Adam. Then receptacle panel, feeder, secondary, match overcap protection device. Okay, so I have my overcap protection device 300 amp. Match the 300 amp. What's 300 amp? 300 amp. Anybody? I have the answer. I need 300 amp. 350. Okay. Now, here's my question for you. What size panel do I have? 300. Is it more than 225 or 200 amp? Yes. Then we start sizing the neutral, cut the neutral slightly. Did you guys hear me? Start cutting the neutral slightly. Hold your horses. Now, yep, these will be 3 conductors. First, number 250 kcm THHN. For the phases. Now let's do the neutral, shall we? Now neutral. The reason why I did this, Adam, because I exceeded the 200. For the neutral, guys, here's what you need to do. Okay, right in here. For the neutral, take the 300 amp. The first 200, leave them alone. 300 minus 200 multiplied by 0.7. I need somebody to do the math for me. So that will be 270, right? 270 amps, right? 270 amps. Then,
Sorry, the 350.
I go by the overcondition device. I'm sizing the neutral.
Yeah.
Yeah, the grad should be 350.
That leg just dropped. 350. This should be 3. Thank you. Not 2. This is 3. You got it? 350? Okay, thank you. So the neutral, so I need to size for 270, guys. Now, the next step, my friend, is take the 270 and take it to table 310.15 B16, 75-degree column. I need somebody to help me, will you? So that would be 1 conductor, number 300, so it's a little bit lower. Number 300, kcm THHN. So my neutral is slightly lower. My neutral is slightly lower.
Does it even work at that point? Like, sizing it down? Because size-wise,
But remember, because we're very close to 200. The closer you are to 200, that's why up to 200, full neutral. The closer you are, I think it's worth. It will get you touch you down a little bit in the copper. Now, if your panel was 400 amp panel, here's what they do in real life. Let me tell you what we do in real life. They don't go higher than 225 amp panel receptacle. So if the load is more, you know what we do? We just put another panel. We separate the panels. Did you guys hear me? The reason for not having a receptacle panel too large, because you're grouping too many eggs in one basket, number one, and voltage drop becomes an issue. So what they do, when we design a receptacle panel, guys, take the whole building. We start cutting the building into sections, and we're going to have 225 amp panel, receptacle panel in this section, another section, a fourth section, and we made a decision, engineering decision, not to go more than 225 amp panel. Did you hear me? And we pull full neutral, and everybody's happy. Now, could it happen that you can go higher than 200, 300? Yes. So that's how you do it. Does that make sense, Derek? Now, say, Chad, you know what? I already bought that wire. I'm going to go buy another size wire. No, I'm going to pull them all 350. Would that be wrong? No. Absolutely not. Okay. Any comments, guys? Any questions about that? So, for the test, you're going to do it this way. With Chad. That's how I want you to do it. Oh, for our panel, no, we're gonna have one panel. We decided to go by one panel. See, these are decisions that you made as an engineer because the project is not too big. We're gonna have one receptacle panel, and whatever the size is, we're gonna do it. I had a group of students last 2 years ago. They actually separated them in two panels, one in the upper level and one in the lower level. If you want to do that, be my guest. I thought it was a good, unique solution. Separate panel, put one in the top, one bottom, feed all the receptacle on the top in the top, and the bottom in the bottom. So they will end up with two panels basically. But then your load calculation have to change. Okay, that's my receptacle panel. Let's go. So now that's basically it, right? We size all these. So that's the last one, the receptacle feeders. So now, Adam, my friend, we have another example where we size, guys, the receptacle panels as well as the, one more time, we have receptacle transformer, receptacle panel, as well as fit from a main panel. Any comments, any questions? I'm going to give you guys 10 minutes. And after that, I would like you to gear up to a UPS. Two examples of UPS. Do you have energy? Do I need to have milk or coffee? Coffee is good. Shall we have 10 minutes and then I need another hour, at least one good hour for the UPS. Shall we? Okay, thank you.